All right. Yeah, so I'll talk about the automated alignment and calibration. So yeah, alignment and calibration, this is different from what Ryan Mind-Shelley did. So he started with a pile of metal and glass and made it into an instrument. I'm talking about after everything was aligned, as well as most instruments would need, then we had to do all the extra fine alignment and calibration to make the chronograph work. So yeah, the main thing here to know is that we're doing high order wavefront sensing control that's model based, which means you have to have a really good model. And that means two things. One, we have to calibrate just about everything. So you have to know the magnification, the rotation, and the translation of all the key optics. So those are the chronograph masks, the deformable mirrors, and also the starlight itself. So that means both where the PSF is in the scale and also in the pupil plane, because we use that as the starting point in our model from phase retrieval. And the phase retrieval is in a different presentation, so I won't get into the specifics of that. And so then for the masks, in the model, we assume they're aligned, which means that we actually have to align them as well to, within one PAM encoder position, which is about a couple microns in the focal planes and around, say, 10 microns in the pupil planes. And unlike so on some of the HCIT testbeds now, there are more automated routines, which are, make things a lot easier in the first place. But unlike a lot of the early milestone tests before we kind of became a real mission, we tried to rely on automated things as much as possible because, when you're running 3 8-hour shifts a day, you don't really want tired eyes like trying to, calibrate images and things by hand. You just want to be able to run a Python script that does it all for you and tells you how much to move or what value to use. So I'm going to just step through some of the, kind of main methods that we used, and hopefully if there's time at the end, talk about some of the things that we didn't expect to happen. All right, so for one of the first things is calibrating the deformable mirrors. We already had measurements of the individual poke gains, so poke an actuator, how much it displaces. But we needed to figure out the rotation, scaling, and translation. So we applied these sparse poke grids, and then did just a SciPy nonlinear model fitting to get the right scale parameters. And you can see that by the end, the pokes essentially disappear when you difference the delta phase that you measure and what you model. So that worked very well. We learned that our initial plan for that in air during the FFT fall campaign didn't work well, so we went back to this way that has worked well in the test beds. I don't have any nice pictures for this because there are kind of a lot of steps, so I'll go through it quickly. But one tricky thing here is choosing the line of sight, because we have a reflective path going to the LOCAM for doing LOFUS stuff, and then of course like the science path going to XCAM for doing HOFUS. And ideally those would be perfectly co-aligned, but they're off by a little bit, and so you have to choose where to put the star, like where to point the beam to make both paths working and as happy as you can. So and then on top of that, you're trying to, we designed the system so that the deformable mirrors should be centered on each other on the pupil image, and hopefully the LOFUS image being centered in its optical path. In the end, we were, I remember it was 100 or say 200 mil arc seconds off the best spot for the two competing HOFUS and LOFUS paths, but it worked out fine. All right, so wavefront flattening. This is one aspect where we found lots of issues in the in-air testing, but we're able to resolve just about all of them for the and are confident we have it down now after TVAC testing. And there's lots of kind of ad hoc things to make it, when you're using 2 deformable mirrors, how to flatten the wavefront at the end. But this is what we measured before, and then you compute what to apply in the DMs and also take out focus with our focus control mirror, and this is the wavefront you expect after. So that's essentially just choosing the DM shapes to get rid of your wavefront error. So that's more or less stuff that we've been doing for a long time. This aspect is somewhat new, and maybe pretty new aspect of the automated calibration. But for doing magnification and clocking measurements, I was able to add in either positions on FPAM and FSAM where we could see 2 masks that were far apart to give us like a long baseline for figuring out the magnification and clocking easily. In between the shaped pupils, I put 2 fiducial 1 millimeter circles that let us do the same thing. So you can, move around the circles until you get the right, in an automated way, figure out the spacing there. And the Leo stop, we had, the funny bow tie shaped openings already there. So we used these to figure out the magnification and clocking in the Leo plane. But this is pretty critical for getting, about, less than 0.1% magnification and say within a milliradian or 2 clocking accuracy. The pupil mask alignments for the Leo stops and shaped pupils is pretty straightforward. It's find the pupil first with ellipse fitting for the outer diameter, and then essentially like a cross correlation for subpixel alignment, but including the fact that you have the pupil in the background rather than just a uniform background. They got very good alignment to pupil masks doing that approach. In the focal planes, in the pupil plane, you have this nice, roughly uniform illumination, but in the focal planes, right, you have a point source, you have a PSF. But fortunately, we have a fast steering mirror that when you raster it, gives you this nice big, what is this, about a arc-second and a half radius, approximate circle uniform background. And so that was very helpful for back illuminating your occulter, and then this has the occulter and the field stop, and so there's still a little misalignment after the coarse alignment. But this was a super useful tool since we didn't have a diffuser to let us back illuminate things. I think on James Webb they'd kill to have something like this to help find where some of the masks are. But fortunately, again, we have lots of moving parts, which helps us out. Speaking of other useful moving parts, we have deformable mirrors. So once you do the coarse alignment for your, and by coarse I mean to within a couple microns. If you want to get sub-micron alignment tolerances on these focal plane masks, we apply sine waves on the deformable mirrors, and then that lets you, it creates spots that are symmetric about the center of the star, and then you move the mask so that you balance the amount of energy within some region of interest on each side of the star. So you can see this is after alignment, you have very good balanced energy, the left and right and up and down when you're moving the focal plane mask. And similarly, when you want to do plate scale measurements and figure out where the star is, right? Because the star is where this plus sign is, but you can't see it. You need to do centroids and stuff on your on these spots that you actuate outside of or in between your field stop and your focal plane mask. So these are nominally like unobstructed, and you can figure out your scaling and star position from those. All right, now for some of the fun stuff. Try to go through these in the couple minutes I have left. There were 3 big surprises. One of them is that here's a grid of all the locam images when we change the pointing of the star in the 233 milliarcsecond steps. And we expected it to look like the nice Roman pupil all the way across, but you can see that it moves off axis, like out of the field of view pretty quickly and looks really bad. I think what we decided the root cause of this, so this is, we decided that, let me back step, we can only use about a 400 mil arcsecond radius. So in the circle where the images still look good and they're still on our 50 by 50 pixel subarray. So we thought it would be more like an arcsecond radius. And we think this is because the LOFUS beam is slightly defocused, and that doesn't affect LOFUS performance when you're still centered, but because of the 3 lens nonlinear design, when you're defocused, it apparently makes the beam fall off quicker and the morphology change much more rapidly than we thought. So again, like fortunately the instrument post vibe seems to be fine, and we use that camera as a quarter to half of this this range. So everything's okay, but just something to keep in mind, when you check one thing at a time, sometimes you can forget to check the mixing effect. A small annoyance is that for surprise number 2 is that eventually figured out from several different effects that our pupil imaging lens doesn't quite image the pupil. It sure looks like it, but you'll notice things like the dead actuator on DM1, you can see it in intensity, but you shouldn't be able to see a phase effect in intensity. So in the end, this just means that for various things in our model, we just need to Fresnel propagate the phase retrieval at this plane by 0.34 meters when you start it in DM1 distances. And then that puts you kind of at the net average, because it's also on a spherical surface. That's kind of the average best position for doing our HOFUS models. But anyway, it's just a minor calibration difference, but easily taken care of. And then here's by far the worst thing that happened. Alignment and calibration went very well in TVAC after after we tested how everything could go wrong with alignment calibration in FFT and then fix them. We were really doing HOFUS for the first time in TVAC. And what I think happened here is that this is the starting phase retrieval, and you see these kind of snake bites on the edge where like the uncontrollable actuator is just outside the pupil, create a very deep spot. So that's, I removed the tip tilt, right? Because tip tilt doesn't really mean anything, and you just want your beam to propagate straight forward. But by removing the tip tilt in the pupil plane, this snake bite kind of skewed it, the PSF by only 0.1 pixels. But then when we created our model-based HLC DM surfaces, after doing that, it pushed the PSF 0.3 pixels off. And then after running it on the test bed, where we had a mismatch where this 0.3 pixels, where 2.3 pixels is 1 lambda over d, like there was a mismatch where the model thought we were off the Coulter, but in the test bed we weren't. It kept trying to correct itself, and eventually we got up to like a third of a lambda over d off after doing wavefront control, which, if you look at the total phase, that's really bad. Like this is a third of a wave. So each time we tried to really do better, we pushed the star farther and farther off axis, and we were having trouble meeting our requirement. So in the end, we started over, and in 2 days ended up beating, our result after we resolved some of these issues by, we had to remove the tip tilt from the Fourier plane. So basically, take the Fourier transform of this, recenter the PSF, and then go back. And then after creating our model-based DM solution for the HLC, again, like recentering the beam to remove any residual tip tilt. So this was completely baffling, I think, to everybody, because we had never seen this before in the test beds. It was extremely frustrating and cost us something like 7 or 8 of our 10 days for doing HOFUS. But fortunately, again, we figured it out and were able to correct it. And, it's all set up to with the software now to avoid this happening on orbit. So again, this is why you test stuff, and fortunately we resolved it. So anyway, I think I'm out of time, but just to summarize here, we fortunately have lots of moving parts on this, which helped a lot for alignment calibration, which we need for the model-based control. And I just want to say that automating these routines was definitely the right call, because you need to be able to just hand off the software for anybody to run on these 24/7 testing campaigns, and just know that no matter who runs it, you'll get the same answer. And I'll say that the last point here, in general, everything worked well that we had tested before in the test beds, and anytime we saw something new or tried to do something too fancy and clever that we'd never done on test beds, that's when we saw problems. So definitely important to test all this beforehand as much as possible. So, all right, thank you.
Online, not quite sure related to this one. If you don't have chance to respond to the question online, make sure that we address those in our JADIS paper. Any quick question from people in the room?
Hey, Dave. The pupil imaging, have you guys thought at all about whether that has any impacts on the FSA fiber measurements that we're going to be planning to use a payload for alignment verification?
I think that's evolved more since I've kind of been in tune with it, but like I think you're saying, like the important things like recording where these aligned positions are, so that when the fibers are in place, we can know whether like where they're landing on these masks and stuff when the instrument's at Goddard, if that's what you mean.
And also, will we still get a good image of the fiber sources with the pupil imaging lens?
Oh, yeah. I mean, it's in terms of how far it's off, again, like, this is the unpropagated one. I think it'll still be more than sharp enough. I guess the concern a little bit is just one of the annoying effects, right, is that since we thought it was at a pupil, when there was a tip tilt at the pupil plane, it shifted this image, which we did not expect to see. So I think that's maybe the main thing I'd be careful about checking. Yeah.
Okay, thank you.